I wanted to talk a little bit about the binomial theorem. What is the binomial theorem? Behold the binomial theorem. Now, I wrote it out in the expanded form and sigma notation, summation form. Now, the expanded form kind of helps us just understand what's going on. And then summation form or sigma notation sums it up. Which, by the way, is sigma notation or summations like when people say, oh, let me just sum this up. I wonder if that's terminology that escaped from mathematics. I digress. Why do we need the binomial theorem? Who cares? Well, I care. And let me show you why. What even is a binomial? It's my understanding that a binomial is a parenthetical statement of two terms and an operator, mathematically speaking. So, like, this is a binomial, a plus b, quantity. What happens if we raise this binomial to a variety of different powers? Well, if we raise it to the power of 0, we're going to get 1, because anything raised to the power of 0 is 1. What if we raise it to the power of 1? Well, a plus b raised to the first power is going to be a plus b. But now what if we raise it to the second power? And we got a plus b squared, which is the same thing as a plus b times a plus b. This shouldn't be too hard to work out. I mean, we could do a times a, which is a squared, a times b, which is a times b, b times a, which is the same thing as a times b times b, which is b squared. And then upon simplification, we're going to get a squared plus 2ab plus b squared. And that didn't take up too much time. What if we have a plus b raised to the third power? Well, that's the same thing as a plus b squared times a plus b. Well, we know, so this is going to be a plus b, and then we know that what a plus b squared is, as we have the answer right here, so we could just say a plus b times a squared plus 2ab plus b squared. And then we could try to work this out here. Now let's do the a terms first. I'm going to say that this is a raised to the third plus 2 times a squared times b plus a times b squared. Let's work out the b terms. So it's going to be, well, the b terms is going to be, and I'm going to do this down here, just because I'm going to end up adding them in together at the end. So this is going to be a squared times b plus a times b squared plus b raised to the third power. And then I'm going to try to add these two together. Let's see, well, a squared is by itself. That's just going to come down. I got 2 times a times b squared, and then a times b squared. So that's going to be, I'm pretty sure that's going to be 3 times a times b squared. Let's see, then we have 2 times a squared times b, and then over here we have a squared times b. So that's going to be plus 3 times a squared times b, and then we got plus b raised to the third. And we were able to get our way through that. You know, we managed. Okay. What if we have a plus b raised to the fourth power? That's going to get a little bit more tedious. And what if we have a plus b raised to the fifth power? What if we have a plus b raised to the 20th power? Okay, now, I mean, unless you would like to spend all day doing that, like, which you could. I mean, maybe you like it, maybe it's good, and it is good for your brain, but what if it's a subsection of a calculation that you're doing? And what if you don't want to use a calculator? What if you can't use a calculator? That's where the binomial theorem comes in. This gives us the power to take, well, it gives us the power to take powers all the way up to whatever number we want. Now, that said, I've written out the binomial theorem in summation notation. Of course, we could just work with it in expanded form, and I think that's what we'll do. Now, the binomial theorem uses combinatorics. Some people say combinatorics. I say combinatorics because Merkin. If we look at n choose k, n choose k, it's not a fraction. There's no division operator. It's just an n over a k, and it's from combinatorics. Well, all it says is that n choose k is equal to n factorial over k factorial times n minus k quantity factorial. To try to help us better conceptualize what's going on, I think it might be worth it to work through an example of like a combinatorics problem. So right up here I'm gonna write n choose k equals n factorial over k factorial times n minus k quantity factorial. And just as like a refresher, for factorials, it's like 0 factorial equals 1 factorial equals 1, 2 factorial equals 2 times 1, which equals 2, 3 factorial equals 3 times 2, which is 6, times 1, which is 6, 4 factorial equals 4 times 3, which is 12, times 2, which is 24, times 1, which is 24. 5 factorial equals 5 times 4, times 3, times 2, times 1, which is 120. Because if you take, well, the way I think about it is like if you have like 25 times 5, that's going to be 125, but then you subtract 5 since you're just doing 24 5 times, so you get 120. I don't know, it's a weird way my brain thinks about it. But so that's what factorials are. The number you're taking a factorial of, you multiply it to every number underneath it, and then your answer is like the combined multiplication of that number and every descending number under it. And fun fact, it grows faster than exponents. So maybe somebody's saying, well, this increases exponentially. You could say, well, does it increase factorially? And then they'll sort of just look at you and you'll be like, this is why I don't leave the house. So we're looking at n choose k equals n factorial over k factorial times n minus k factorial. Imagine like you have a bunch of fruit. You have 4 types of fruit. N equals 4. Say you have um, A, which equals apple, so you got an apple. And then you have B, which is banana. And then let's say you have an orange, and then you have a peach. And you want to choose a pair of 2 fruits, right? Say like you want a snack, and you're like, okay, but I'm only gonna have 2. And so in this case, if you want 2 of them, that would mean that R equals 2. You're choosing 2. N choose 2. You're choosing 2. So K equals 2. The question is, how many different combinations are there of the fruit pairs that I can get? How many unique pairs of fruits can I make? What are all of the combinations of fruits that I could have if I am to pick 2 out of a pool of 4? I'll choose 2 fruits. And so what are all the combinations I can get? Well, let's use this formula. So our n is 4 and our k is 2. So now we have 4 fruits and we're choosing 2. 4, choose 2. And so we're going to apply this to our formula here. 4 factorial over k factorial, k is 2, so 2 factorial times 4 minus 2 quantity factorial. Something that I think might be worth mentioning at this point in time is the order of operations. Well, we know PEMDAS. This is parentheses, exponents, which includes factorials and functions. Functions being like sine of x, trigonometric functions, logarithmic functions, and things of that nature. M, multiplication, and D for division. But we write it like this because neither one of them have precedence over one another. The only thing that we need to note for multiplication and division is that we move from left to right. And then we have addition and subtraction, but the same thing as before, neither one of these operators have precedence over one another. It's addition and subtraction, but we do move from left to right. Well, 4 factorial, 4 times 3 is 12, times 2 is 24, times 1 is 24, so we're going to have 24 over 2 factorial. Well, 2 factorial is just going to be 2. Then we do parentheses first, so we're going to have 2 factorial. Oh, this is going to be 24 over 2 times 2, which is going to be 24 divided by 4, which is just going to be 6. That means that there's going to be 6 unique pairs of fruits that we could choose for our snack. So we could write out our 6 different pairs, right? So um, well, we could have an apple and banana. We could have an apple and an orange. We could have an apple and a peach. We could have a banana and an orange. We could have a banana and a peach, and we could have an orange and a peach. Or we could have an orange and a peach for our 6 different combinations. But note, like, if you picked something like BA, like a banana and an apple, that's the same thing as an apple and a banana. So we don't count that one. We just write in an apple and a banana. It's the same thing as it's you don't count it twice. The order does not matter. Um, And why does this show up in binomial theorem? Well, it shows up in the binomial theorem because the binomial theorem tells us how to expand on an expression like a plus b quantity raised to the nth power without having to manually multiply parenthetical statements together for hours and hours and hours. I mean, it's only going to get more complex. How about we work through a couple of examples of us using the binomial theorem to raise binomials to different powers? It's worth trying to understand this in sigma notation because it quite literally sums it up in a way that's, well, it's very small and it's quite efficient. Let's try to bridge the gap between the summation form and the expanded form mathematically. So before we get started with the example, I just want to explain the summation notation. So we have a plus b quantity raised to some power n. Note the presence of n on top of the letter sigma. So we start at k equals 0. It's saying that we're going to start at k equals 0, we're going to stop at n. We're going to run it through n choose k, which is the coefficient that goes in front of a raised to the power of n minus k times b raised to the power of k. So let's work through an example using the summation notation. Ignore the expanded form for now. Let's say that we don't have a plus b raised to the second power memorized. Let's say that we don't know that it's a squared plus 2 times a times b plus b squared. Let's say that we didn't memorize that. All right. So how could we come up with this answer using the summation form? So we're going to have a plus b squared equals the summation starting at k equals 0 all the way up to n. Okay, but in this case, n equals 2. So this is going to be for the function n choose k, but remember, n choose k is the coefficient of a raised to the power of n minus k times b raised to the power of k. So I'm not even going to draw an equal sign. I'm just going to start plugging stuff in. So we're summing numbers from 0 to 2. That means that we're going to start at k equals 0. So we have n, in this case 2. 2 choose 0, okay, because k is set to 0, n is set to 2. For a raised to the power of n, which is 2, minus k, which is 0. So that's just going to be 2, but we're going to leave it as such for now, times b raised to the power of k, which in this case is 0. Cool, but we're going up to 2. So now k is set to 1 because we're counting upwards, and we're going to sum this, so it's going to be plus n, which is 2, choose 1 because we already did 0, but we're counting up to 2. So 2 choose 1 times a raised to the power of n, which n is set to 2, minus k, well, k is set to 1, so 2 minus 1 times b raised to the power of k, and that's 1. All right, one more here. We just got one more because we're counting all the way up to 2. So now we have 2, which is n, choose 2, which is k, because we counted up from 0, 0, 1, 2, and here is where it indicates to stop. So 2 choose 2 times, because remember this is the coefficient, a raised to the power of n, which is set to 2, minus k, which is set to 2. So a raised to the power of 2 minus 2 times b raised to the power of k, which in this case is set to 2. And that's where we stop because we're supposed to stop at 2. Just going to move this up. Don't let these n choose k's like freak you out. Like all these are our coefficients. That's a coefficient, that's a coefficient, and that's a coefficient. Moreover, we literally have the definition of what n choose k is right up here. Okay? So that means that we can find our coefficient values. There's 3 of them. The first one is 2 choose 0. Well, 2 choose 0 by definition, if we look up here, that's the same thing as 2 factorial over 0 factorial times 2 minus 0 quantity factorial. Well, the factorial of 2 is 2. The factorial of 0 is 1. The 2 minus 0 is 2. And the factorial of 2 is 2. So we're going to have 2 over 2, and that's just going to equal 1. And so this coefficient is done. Now let's work on this coefficient, 2 choose 1. 2 choose 1 is going to be 2 factorial over 1 factorial times 2 minus 1 quantity factorial. 2 factorial is 2. 1 factorial is 1, so it's going to be 1 times, well, 2 minus 1 factorial is going to be 1. So it's going to be 1 times 1 on the bottom, it's going to be 2 over 1, which is going to equal 2. For this third coefficient, 2 choose 2, let's see, it's going to be 2 choose 2 is equal to 2 factorial over 2 factorial times 2 minus 2 factorial, which is the same thing as 2 over 2 times 1, which is just going to be 1. So now we're just going to take this and we're just going to fill in what we found our coefficients out to be. Well, the coefficient for 2 choose 0 is 1. That means that we're going to have 1 times a raised to the power of 2 minus 0, which is just a squared, times b raised to the power of 0, which is just going to be 1, plus 2 choose 1. 2 choose 1, we found 2 choose 1 to be 2, so it will be plus 2 times a raised to the power of 2 minus 1, which is just going to be a, times b raised to the power of 1, which is just going to be b, plus 2 choose 2, which is the coefficient for this term here. 2 choose 2, well, we found 2 choose 2 to be 1. So we're going to have 1 times a raised to the power of 2 minus 2, which is going to be 0. So a raised to the power of 0 is just going to be 1. So we'll have 1 times 1 times b squared. And then with a little bit of simplification, we can see that we're going to have a squared plus 2ab plus b squared. This is the same thing as what we have above. And that's how you would work that out with sigma notation. Let's say that we want to know what a plus b quantity raised to the 4th power is. Well, we can use the binomial theorem to figure out the answer. I have written out the binomial theorem in sigma notation, and I will now proceed to write it out in its extended form. But I will derive it from sigma notation. So to write this thing out in expanded form, we can use the sigma notation. We want the sum of this expression all the way up to the number n. So first we have to write the first coefficient. That is n choose 0 because k equals 0 and we're starting at 0. So k choose 0 times a raised to the power of n, because in this case it's going to be n minus 0, times b raised to the power of k, which in this case is just going to be 1, so we don't even have to write that in. Plus, what's up next? The coefficient value for k equaling 1, because 1 comes after 0, so we're going to have n choose 1 times a raised to the power of n minus 1 times b raised to the first power, which is just b, but we could write in a 1 if we'd like, plus the second binomial coefficient, which is going to be n choose 2, because 2 comes after 1, times a raised to the power of n minus k, which in this case is 2, times b raised to the power of k. Oh yeah, but k is going to be 2. So k is set to 2. So I'll just write in a 2 right here. And then we're just going to follow this pattern all the way up to some value n choose n times b raised to the power of n. All right, so bringing it back to what we have a plus b raised to the 4th power. So in this case, we could write this in sigma notation. K equals 0, and we're going up until n equals 4. And so we'll have the coefficient being denoted as n choose k for each partial sum times a raised to the power of n minus k times b raised to the power of k. A plus b quantity raised to the 4th power. We have to find our first coefficient. We're starting at 0. So, well, we're going all the way up to n. So it's going to be 4 choose k, which in this case is 0 for the first partial sum, times a raised to the power of 4 minus 0 times b raised to the power of 0 plus, we're going to have our second partial sum, so it's going to be 4 choose 1 times a raised to the power of 4 minus 1 times b raised to the power of what k is, and in this case, for the second partial sum, it's going to be raised to the power of 1. And so that's going to do it for the second partial sum. For the third partial sum, that's going to be 4 choose 2 times a raised to the power of 4 minus 2 times b raised to the power of 2. And that's going to do it for the third partial sum. For the fourth partial sum, it's going to be 4 choose 3 times a raised to the power of 4 minus 3 times b raised to the power of 3. And that's going to do it for the fourth partial sum. For the fifth partial sum, that's going to be 4 choose 4 times a raised to the power of 0, because, well, I'll write it in 4 minus 4 times b raised to the power of 4. We'll hit this with a simplification. Now, as we know, a raised to the power of 4 minus 0, well, that's just going to be a raised to the 4th power. The b raised to the power of 0 is 1, so we're just going to ignore that, plus 4 choose 1 times a raised to the 3rd power times b raised to the 1st plus 4 choose 2 times a raised to the 2nd times b raised to the 2nd plus 4 choose 3 times a times b raised to the 3rd plus 4 choose 4 times a raised to the 0 power, which is going to be 1, times b raised to the 4th. So now what we have to do is we have to find the binomial coefficients, that is n choose k, each coefficient. So here's a binomial coefficient here, and here, and here, and here. And we'll start with 4 choose 0. And if we look up here at our formula, well, n choose k equals n factorial over k factorial times n minus k quantity factorial. So that's going to be, so 4 factorial over 0 factorial times 4 minus 0 factorial. So that's going to be 24. Well, 0 factorial is 1. 4 factorial is 24. So we're going to have 1 times 24 in the denominator. It's just going to be 24 over 24, which is just going to be 1. All right, then we have to do our second binomial coefficient, which is going to be 4 choose 1. 4 choose 1, it's going to be 4 factorial over 1 factorial times 4 minus 1 factorial, quantity factorial equals, well, 4 factorial is 24. 1 factorial is 1. 4 minus 1 is 3, and 3 factorial is 6. So we'll have 24 divided by 6, which I do believe is 4. The binomial coefficient for our third partial sum is going to be 4 choose 2, and that's the same thing as 4 factorial over 2 factorial times 4 minus 2 quantity factorial. That's going to be 24 over 2 times 2, which is going to be 24 divided by 4, which equals 6. And then we have 2 more coefficients to find. That is the coefficient for our fourth partial sum. It's going to be 4 choose 3. That's going to be 4 factorial over 3 factorial times 4 minus 3 factorial. That equals 24. Well, 3 factorial is 6. So it's going to be 24 over 6 times 1, which is going to be, well, times 1 factorial, which is going to be 24 over 6, which that's going to be 4. And then for our final binomial coefficient for our, what is this, our fifth partial sum, that's going to be 4 choose 4 equals 4 factorial over 4 factorial times 4 minus 4 factorial. So this is going to equal 24 over 24 times 0 factorial. 0 factorial is 1, so this is going to be 24 over 24, which is 1. So now we have all of our coefficients. We have the coefficient for our first partial sum here, the first coefficient for our second partial sum here, our coefficient for our third partial sum here, our coefficient for our fifth partial sum here, and our coefficient for our sixth partial sum here. And so we can just plug this all back into everywhere where we see the n choose k. That means that I can assert that a plus b quantity raised to the fourth power equals, well, 4 choose 0 is 1, so I'm not even going to bother writing in a 1. I'm just going to write a to the fourth power plus 4 choose 1, and 4 choose 1 was identified to be 4, so we're going to have plus 4 times a raised to the third power times b plus 4 choose 2, which was identified to be 6, so we're going to have 6 raised to, 6 times a raised to the second power times b raised to the second power, and then we're going to add that to 4 times a times b raised to the third power plus 4 choose 4, which was identified to be 1, and, well, 4 choose 4 is attached to b raised to the fourth power, so we're just going to have 1 times b raised to the fourth power, which is just going to be b raised to the fourth power. So in conclusion, a plus b raised to the fourth power is going to be equal to a raised to the fourth power plus 4 times a raised to the third power times b plus 6 times a raised to the second power times b raised to the second power plus 4 times a times b raised to the third power plus b raised to the fourth power. And that's going to be your answer. And we can do another one. Now it's like, say that we want to find a plus b quantity raised to the fifth power. Well, our sigma notation will look like this. This is the case where n equals 5. And let's just try to see, like, what's our setup going to look like? K equals 0, but n is 5. So we'll have 5 choose 0 as the binomial coefficient for the first partial sum. Then we're going to have, let's see, a raised to the power of n, which in this case is 5, minus k, which is 0 for the first partial sum, times b raised to the power of 0, plus 5 choose 1, and note that how we're just counting up here. We're just counting upwards from 0. And then 5 choose 1 times 5 minus 1. 5 choose 1 times a raised to the power of 5 minus 1 times b raised to the first power. Then for the third partial sum, well, we're going to have 5 choose 2 times a raised to the power of 5 minus 2 times b raised to the power of 2. For the fourth partial sum, we're going to have 5 choose 3 times a raised to the power of 5 minus 3 times b raised to the power of 3. For the fifth partial sum, we're going to have 5 choose 4 times a raised to the power of 5 minus 4 times b raised to the power of 4. And then for the sixth and last partial sum, we're going to have 5 choose 5 times a raised to the power of 5 minus 5 times b raised to the power of 5. At this point, let's just hit it with a simplification. Well, 5 minus 0 is 5, so we're just going to have a raised to the fifth, b raised to the power of 0 is just going to be 1, so that's going to do it for the first partial sum. For the second partial sum, we're going to have 5 choose 1, that's going to stay the same. Well, 5 minus 1 is going to be 4, so we'll have a raised to the fourth power times b plus 5 choose 2 times a raised to the third times b raised to the second plus 5 choose 3 times a raised to the second and well, b's raised to the third plus 5 choose 4 times a raised to the first, or just a, times b raised to the fourth plus 5 choose 5 times b raised to the fifth. What are the binomial coefficients? What is 5 choose 0? Well, per our formula here, we could see that 5 choose 0 is the same thing as 5 factorial over 0 factorial times 5 minus 0 quantity factorial, I think, and then, well, 5 factorial, 120, well, 0 factorial is 1, so we're going to have 1 times 5 factorial, which is 120 over 120, which is just 1. Now for, well, 5 choose 1, that's going to be, well, that's going to be 5 factorial over 1 factorial times 5 minus 1 quantity factorial. 5 factorial is 120, and then 1 factorial is just going to be 1 times, this is going to be 24, because it's going to be 4 factorial. 4 factorial is 24, I'm pretty sure, because 4 times 3 is 12, times 2 is 24, so it's going to be times 24, and 120 divided by 24 is 5. Next up, we're going to have a 5 choose 2. So 5 choose 2 is going to be 5 factorial over 2 factorial times 5 minus 2 factorial, which is going to be 3 factorial. So this is going to be 120 over 2 times 6, I'm pretty sure. And that's the same thing as 120 divided by 12, which is, I'm pretty sure the answer is going to be 10. Next up, we're going to have 5 choose 3. Well, 5 choose 3, that's the same thing as 5 factorial over 3 factorial times 5 minus 3 quantity factorial, which is the same thing as 120 over, what's 3 factorial again? I think it's 6, times 2 factorial, which is just going to be 2. So we're going to have 120 over 12 again, which is going to be 10. Next thing, we're going to have 5, for the next binomial coefficient, we're going to have 5 choose 4. Let's see, there's 5 factorial over 4 factorial times 5 minus 4 factorial, excuse me. Well, 5 factorial we know is 120, 4 factorial is 24, times 1 factorial, which is 1, so we're going to have 124 over 24 is 5. Next up is 5 choose 5. Well, 5 choose 5 is the same thing as 5 factorial over 5 factorial times 5 minus 5 quantity factorial, which is going to be, well, 5 factorial over 5 factorial, because 0 factorial is 1. This is the same thing as 120 over 120, which is the same thing as 1. So now we have all of our coefficients that we need. We could just plug these in. 5 choose 0, we found that to be 1. 5 choose 1, we found that to be 5. 5 choose 2, we found that to be 10. 5 choose 3, we found that to be 10. 5 choose 4, we found that to be 5. 5 choose 5, well, that was 1. Well, I believe that that means that a plus b quantity raised to the fifth power equals equals a raised to the fifth power plus 5, because that's our coefficient for 5 choose 1. 5 times a raised to the fourth, and just remember, I'm just plugging everything in here, plus 5 choose 2, which is calculated to be 10 times a raised to the third times b raised to the second plus 5 choose 3, which is calculated to be 10 times a to the second times b to the third plus 5 choose 4, which is going to be 5 times a times b raised to the fourth power plus b raised to the fifth. So a plus b quantity raised to the fifth power equals a raised to the fifth plus 5 times a raised to the fourth times b plus 10 times a raised to the third times b raised to the second plus 10 times a raised to the second times b raised to the third plus 5 times a times b raised to the fourth plus b raised to the fifth power. And so that will be our answer. Thank you guys so much for watching. I really appreciate it, and have a good day.